So here's the thing. So that's why it's like a thought experiment. We only have to multiply the matrix we want to get the result. Okay. So if we transpose it, we get 1, 3. We multiply 1, 3 from the left, of course. I told you we'll throw us an error. Okay. Are you with me?
Yeah.
Because this doesn't match with this. Okay. So what's happening is the simplest way is to do a for loop. So what you can do is for little a, in capital A, suppose this is the tensor that is storing this. Then what happens is, if we do this, it loops in the first dimension of dim 0. And this is okay. But yeah. But still, the goal is that we should be able to manually verify. Okay. A PyTorch's output is working supposed to theory. So let's say this. How do we check if a machine learning algorithm is correct? If we answer, oh, it converges, it's correct. The answer is no. Okay. We should be able to, for example, check its gradient. See if the gradient, is working toward our favor. So that's why, this is like some advanced technique. It's not advanced, but we ought to know it. Okay. So actually, PyTorch, even with itself, it has various tests. So if you dig into PyTorch, it has this unit test. It has tests. So every time, for example, I'm a contributor. Every time I submit a pull request, and the GitHub will run like 100 or something tests. So you gotta pass these tests. For example, your change wouldn't change the original software structure of it. Okay. So how do we verify it? We create these tests to verify our algorithm is working as it's intended to. So this is the purpose of problem 5. But yeah, let's back to conjugate gradient, and then so after we present it, so we won't show the convergence today. It's quite long because it involves something called Krylov subspace. So it's highly related to something called Kalman filter, and basically it's like everyday engineering uses Kalman filter to do weather forecasts, GPS locating, etc. But okay, so let's recall what conjugate gradient does. Okay. So by right now, we should be pretty familiar with the setting. That is, we want to minimize this quadratic function. Q is a symmetric matrix, and Q is also positive definite, so SPD. Okay. And our goal is to find the unique local minimizer of that. So for example, I see several of us tried the optional problem in homework 1, but the whole point of the optional in homework 1 is not show, okay, your solution is this. Actually, if you read the problem, it shows the local minimizer is unique, which we mean we need to show the solution is unique. Okay, so how to show the solution is unique? So that's your question. But okay, let's back here. And for this, we want to find the unique local minimizer, and to solve this problem, it's equivalent. Okay, because of the second order condition, the Hessian of this is positive, so we only need to solve a critical point. Okay? So it's equivalent to solve this, and if we solve this, we'll get X star is a unique local minimizer, and it is the solution, let's say solution to Qx equals B, okay, this matrix equation. So now we need to project to the space, which we call Krylov subspace. But we didn't learn the name yet, but the idea is we project to a subspace. So we search, okay, the minimum in a subspace. Okay. So this is the idea. Versus earlier what we had, line search. We search the minimum on a line and then we proceed. Okay, so now we search. Okay, we call it S sub k, and it is a span of actually k plus 1 vectors. Okay. So it's d0, d1 up to dk. And moreover, so these are the bases, and so these are the bases, and we want these basis vector to be Q orthogonal. Okay. So what's happening is what we want is the I is Q orthogonal to dj. And this means the I Q inner product with dj is 0. And Q inner product can be also rewritten as the L2 inner product. Q inner product is, we have two vectors, x, y, doing Q inner product is Qx inner product with y, it's also x transpose Q times y, and this is the inner product only when Q is SPD. So what we want to do is we want to minimize, okay, so the distance so we want to find our xk plus 1 in the space of our initial guess plus this such subspace. We minimize its distance to the unique local minimizer in the Q norm. Okay? The reason why we do this is because it's our right identity here. The reason we do this is for this specific function, okay, f of x subtract f evaluated at x star is 1/2 x subtract x star measured in Q norm squared. I mean, this is an important identity. So it tells us to minimize this quadratic function, it's equivalent to minimize the distance of our current iteration to this local minimizer. But the distance is Q distance, which is induced by this Q norm. All right. So now we have this. So we want to minimize. Instead of a minimize, the next iteration along the line, we minimize it in the subspace, and this subspace is expanding. So, and this, if we draw the figure, in the context of optimization, instead of a pure geometric projection, what we have, this is our initial guess, okay? So this is our S. So our initial guess may be here. And we want to search along this S such that our K plus 1s iterate. Okay. So originally, the vector points, for example, this is origin, okay, is here. This is our initial guess. And we search along this subspace S sub K to get this. And what we want is we project this X star to this SK, okay? So what's happening is X K plus 1, subtract our initial guess, is equal to the projection onto S. Okay, so S is, let's just in short, S defined as S sub K, and the projection, but in the Q norm. And this is X star subtract our initial guess. So this is basically the story so far. Okay. And our goal is to build an efficient. So let's recall the definition of projection. Okay. So let's recall the definition of projection. The definition of projection is for U in Rn. The projection SQ of U is an S such that it satisfies the following. That is, projection in Q, U against V in the Q norm, okay, is equal to U inner product with V, but in the Q inner product for any V in S. This is Q projection, or it's sometimes called Q projection. So this is the whole story. That is, we search the minimum in a subspace, and the action of searching the minimum in the subspace is equivalent to projection. So projection is equivalent to minimization, which is equivalent to, like subspace searching. And so all these are like intertwined and related. Okay, now, so our goal is to build an algorithm based on this projection. So we need a lemma. Okay, so the next is, so we want to build an efficient algorithm based on this. So before we present the lemma, so let's recall how did we proceed. So what is the CG's idea? Okay. Remember, we already assume we have a basis. The question is how to build the basis. Okay, so the idea is, suppose we have a Q orthogonal subspace S sub K. Okay, we do subspace search. Okay, we do projection, and then we get the K plus 1 iterate. Okay. So now we have xk. Now we have our initial guess, but then we have this d0, d1 up to dk. Okay, so we have a K plus 1 subspace. So we project our initial guess to this subspace to get xk plus 1. Okay, so now we have Now we have the gradient vector, which is defined by this. All right. So next is we have a set of bases, right? So we know that the first K plus 1 basis let me make sure my indexing is right, because I don't like this. Now we just add the negative gradient. Okay. We just want to add this negative gradient, which is our current, where our function decreases the fastest direction to the basis of this subspace. And what we do next is we do Gram-Schmidt orthogonalization to this, and then we get a new subspace that is Q orthogonal again.
I have a question. Just to confirm, the D's in the first basis and the D's in the second basis are not necessarily the same thing.
No, they're the same thing.
Oh, but the G turns into something else.
Yes.
Okay.
That's so. So what happens is we want to apply Gram-Schmidt, right? So suppose currently the blackboard is spanned by 2 orthogonal directions. Okay. So a third direction comes, it may be this, and we want to orthogonalize it to be orthogonal. Okay. This is like a orthogonal using the manila inner product. But here we want to orthogonalize Gram-Schmidt. We apply Gram-Schmidt procedure in the Q inner product. Okay, the looking type inner product. All right. So they are the same thing. Okay. That's why CG is so efficient. Okay, because the first K plus 1 basis it doesn't change. Okay. I mean, we actually don't want to change it. So efficiency. So later on we will see why this is efficient, because CG actually it was invented like 60 years ago. I forgot, but it was invented by engineers, and like the cleverness of this method is it doesn't require lots of storage. You know, back then the storage was pretty limited. Like people can't afford to store all vectors along the trajectory of this optimization. Okay, so they don't want to change these bases. But the thing is, even if we don't store these bases, the optimization is still done in an ever increasing like dimension subspace. So that's pretty, I mean, awesome if you're asking. So when I learned CG, I mean, 20 years ago, 17 years ago, I was totally blown away, you know, so by the cleverness of these engineers. And okay, so to present the CG, we need a lemma. All right. So the lemma says the following. The lemma says if we did perform the projection into this orthogonal subspace, okay? So where S sub k, okay, so where S is defined by this S sub k, which is span of these q orthogonal vectors or directions is q orthogonal. Okay. Then so what's crazy about this is then for the gradient direction evaluated at this point, okay, we have the following two things. The first one, is this gradient vector is orthogonal to all previous directions. So this is a vanilla inner product, no Q here. Okay, this is the first.
Why?
We're going to show it.
Oh.
Right? So this is something about math class is after we present the result, we have to prove it to understand why it is the case. So think about how crazy this is. The steepest descent, okay? So we learned that okay, so this is true. So for steepest descent is like the gradient of consecutive iterations. They are orthogonal. Okay. So for steepest descent is like this is a gradient at k plus 1th iteration. This is a gradient at kth iteration. So the search direction is orthogonal between consecutive iterations, but it doesn't tell us about previous iterations. So this orthogonality is for all previous iterations. And the second thing, which is the key to get the state of the art for this problem is it's also Q orthogonal. Okay? It's also Q orthogonal, but to all previous vector except one, okay? All right, so let's look at the formula, the difference. So this is to k, okay? The Q orthogonality, wow. I guess I'm the only person who still uses markers to lecture on the board because the marker I got from our school, it's either dried up, but it's new, still new in the box, but it's already dried up, I guess. For a couple of years, no one's used this lecture. Wow. All right. So now we're going to show it. I mean, it's not too bad to show this. Okay. So I want to reserve half an hour for our homework. Okay. So. The first one is not too bad. Okay. The first one is we simply write down what this is. Then we'll see. It's actually true. Okay. So. So let's still recall this. So even though this will be given as the formula in the exam, but by now, so if Q is SPD, we should be pretty familiar with the gradient. That is Qx subtract B. Definition. That's simply Q. Okay. That's when Q is symmetrical. So then this is okay. Well, we have also to acknowledge that B is Q times X star. Okay. So then if we look at this formula, G K plus 1's iteration, gradient at K plus 1's iteration, inner product with DI is, just replace it, right? Q X K plus 1 subtract X star against the I. First step. Then we rewrite it as the inner product. With subscript Q by definition. Okay. So this is definition of the inner product of Q, which is right there. Now we're already done. Why? We look at this formula. Okay. So X K plus 1 subtract our initial guess is a projection onto this subspace S, but with Q projection, and this is X star subtract X0. So this is equivalent. So this is the equivalent of saying, so this is a projection, right? We just use this definition. That is, an equivalent definition of this is, okay, this Q inner product against a vector in S is equal to X star subtract X sub 0 Q inner product with the same vector V for any V in this subspace S. Okay. Now if we subtract this to the left, we get X k plus 1's iteration, subtract our initial guess inner product against the v, but in the Q norm is 0 for any v in Sk. Okay. Now we compare. Sorry, this is x star. Okay. X0 got cancelled. Okay. So x initial guess got cancelled, and we have this is xk plus 1's iteration, subtract our unique local minimizer, and we inner product of this difference against any v in this S subspace, its Q inner product is 0. Okay. Now we take a look back at this. So this is 0. Why? It's because di I from 1, 0, 1, 2, etc. up until k are the basis of S sub k, right? Because of this. For any v, for any vector v, this Q inner product is 0. So I mean, of course, the Q inner product with the basis is 0. Okay. So now we have shown so now this is like part 1. So part 1 is proved. So now we move on to part 2. So to prove part 2, we need to acknowledge that. So to prove part 2, we need to acknowledge that this formula can be made in a very recursive fashion. Why I'm saying this is, so we seek x k plus 1 in, okay? So it's like this is our initial guess, and our initial guess is plussed with a vector in this search subspace. So this is like this search subspace determines where we move from our initial guess, okay? So now this just says that, okay, this just says what? This just says, so I mean, these two are actually equivalent. That is, the increment is in the in the search subspace, but this search subspace, so this is from 0, has a basis, right? You know the basis, that is, because S is the span of these bases. So now, to think about this, when k is 0, okay, x1 equals x0 plus alpha 0 p0, right? So now let's look at x2. Okay, x2 is x0 plus alpha 0 p0 plus alpha 1 p1. And what is this? This is x1. So we can make this formula recursive. We don't have to write down this sum with alpha I, with k plus 1 alpha I multiplying with all these bases. We can do all right. So we just keep track of x0, x1, x2, and etc. Okay. So we have this is x I plus 1 equals x I plus alpha I is from 0, 1, 2, up until k. I don't want to erase this. Yeah. Okay, but just okay. So if I mention this in lecture, just look back at our notes that we did the Grand-Schmidt. So now let's decompose this formula. Okay. But first we have to acknowledge this. Okay. But then, if we simply write so we have also this, right? Okay. So alpha I is a number. Okay. Alpha I is like our learning rate. It changes at every iteration, step size, whatever. We multiply Q on both sides. So the matrix Q can go through alpha I and directly multiply with this D sub I. Yeah, let me still do. Okay, yeah, let's still do this. Now we're gonna play some simple algebraic trick. That we have used often too many times. That is, we plus something, then we minus the same thing. Okay. So we rewrite the right side as subtract b, then we plus b, but then if it's a plus, if it's plus b, it's a minus minus b, so alright. So this is where magic happens, that then this becomes the difference of gradient. So okay. What is this? This is G I plus 1 subtract G G superscript I plus 1 and G I. So okay. So these two are the gradients at I plus 1's iteration and I's iteration. So using this algebraic trick. Now this I. So let's keep track of this 0, 1, 2, okay, up until k. All right. So however, let's write down the last two, because what we care is the k plus 1 and k. Okay. So we write down the last two iterations. So when I is k, this is alpha k q dk equals g of k plus 1 subtract gk. Okay. So this is a newly added vector we want to orthogonalize. Okay. So that's why we don't want to. So this is a newly added vector to this d0 to dk. We want to do Grand-Schmidt with this vector. So this vector is not yet, okay, in in this space yet. All right. So otherwise, you know, it's optimized in the same subspace. It doesn't improve our result because in previous iteration we already found the minimum in this search subspace. So if we want to improve our result, we need to add something that is linearly independent with all these directions. Otherwise, we're searching the same subspace. Okay. So without loss of generality, we can assume our k+1 iterations gradient is not in our subspace. Otherwise, we're doing repetitive work. Okay. So let's look at this formula. So this is not in S yet, but this is already in S. Now, if we move the index further back one iteration, okay. So if we move the index further back one iteration, we'll see this alpha k minus 1 q b k minus 1 equals is equal to g of k subtract gk minus 1. This is in our SK. This is in our SK as well. So think about how our SK is built. It's like, okay, so when at iteration 0, so we get our first gradient and we set it, and we set, you know, the first search direction to be our negative gradient. And then at second iteration, we get a new gradient. Okay? And then we Grand Schmidt to get D1 such that they are orthogonal. Same thing at iteration. So iteration 1, iteration 2. So we get a new gradient, okay? And we add this gradient to D0, D1, okay? And we Grand Schmidt, we orthogonalize it to get this new Q orthogonal direction D2. And it goes on. What it tells us is, the gradient, okay, this subspace is actually built from the gradient. That is, the span of D0 up to Di is actually equal to span of G0 to Gi. Okay, so I from 0, 1, blah, blah, to k, up until then. So by this, the right-hand side of this, okay, is in our search subspace S sub k. Okay, but not that. This is in SK, so this is not. Okay. So if this is in SK, we just use property number 1. Okay. So by 1, by 1. By 1, this is true. I mean, because this inner product with every basis in S, we have inner product 0. So this guy is orthogonal to S. Now we just let V, so this implies V, we just let V to be this guy. Okay? So we just let V to be alpha K minus 1 Q, BK minus 1. Because this is in SK, okay? It's a difference of the gradient, so it's in SK, so this is 0, all right? This index can go on and on if we move further back. So if we move further back in the index, G of K minus 1 subtract G of K minus 2, it's in S as well, so we have, this is okay. Okay. Now we have a Q here. So because Q, so X, QY, X inner product with QY is the same thing as QX inner product with Y, and this is nothing but XY Q inner product. Okay. So if Q is symmetric. Now, so all these becomes, so that then this implies GK plus 1, okay, Q inner product with DI is 0, but this I only goes up to K minus 1. Okay. So I 0, 1, 2, dot, 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 K minus 1. Because the best orthogonality we get about this is up to K minus 1, because when we add a new gradient here, it's not in our SK anymore. Okay. So now we've shown theorem. We've shown the lemma. So these orthogonality gives us a huge leverage of when we try to build an efficient algorithm. The reason is because, okay, so now let's back to the Gram-Schmidt orthogonalization procedure. Okay, so these are Q orthogonal already. Okay. So the previous K plus 1 vector are Q orthogonal already. We add a new vector here. So by the way, this alpha K, okay, so here with loss of generality, we assume alpha K minus 1, alpha K minus 2, and up until alpha 0, they are not 0. So if we have a step size that is 0, it just means we can stop, because we already reached the minimum. So without loss of generality, we just assume we haven't reached. So this just means the equivalent saying xk is not our local minimizer yet. Okay. So if xk is this, then we just move back an index and prove things for starting from k minus 1. So now let's back to this orthogonalization. So we add a new vector to this set. We want to orthogonalize it. Okay. And what we do is we write, the new one as. So we start from this vector. Okay. And we don't have to multiply a constant to this vector. It's because if we multiply a constant, we can always modulo that constant. So let's start from here. Okay. Plus, and we use a special index, beta, for the kth direction because of part 2 in this lemma. So the Q orthogonality only goes up to k minus 1. Okay. And this is plus alpha. Yeah, I use gamma. Gamma dk minus 1. Okay. Plus gamma k minus 2 dk minus 2 up until gamma 0 d0. So this should be pattern 9, 10, 11. Okay. Now we just make what we do. We inner product, but in Q inner product with dk on both sides. So if we do that, we have dk plus 1 inner product with dk, but the Q inner product, because we have to require the k plus, we want to do Gram-Schmidt. So this vector, so we want this quantity to be 0, because that's our goal, okay? Our goal is to make this vector being Q orthogonal with this. So we set this to be 0. Right? Now if we look at the right, we have this is minus the k plus 1's gradient, inner product, with dk. dk is known, okay, Q, plus beta dk, Q inner product, with k itself, and the summation of I from 0 to k minus 1 gamma I di inner product with dk Q naught. All these are 0. So I only goes up to k minus 1. So all these are 0. So now we obtain this. We obtain this equation. So the left side is 0. What's we left is this guy equal this guy. So now we've solved beta. So this implies beta is, so we plus this to the left. Beta is nothing but the k plus 1's gradient inner product with the kth direction. Okay. So, and the kth direction inner product with itself in the Q. Okay, so we found this coefficient in the Gram-Schmidt orthogonalization. What we need to find is the rest, gamma. So now what we want to do is we inner product this equation both sides with we do Q inner product. So we do Q inner product with BI for I is 0, 1 till k minus 1. So let's see what we get. Again, the left side okay, so the left side is 0 because we want this vector to be orthogonal with this vector. Now let's look at the right side. Okay. Now let's look at the right side. Okay. So the left side is we want. This is what we want. This is a goal of, so this is what we want in the Grand-Schmidt. We want to orthogonalize. We want to make a k plus 1 basis orthogonal to all previous ones. Okay. This term looks familiar, isn't it? This is 0 by the part 2. Okay. This is dk. dk is an orthogonal basis in Q, so it's orthogonal to di. I is not k, okay. This I is taken up to k minus 1. So this term is 0 because we already have a Q orthogonal subspace. Okay. So there's a sum here. And this sum runs from j from 0 to k up to k minus 1. Okay? So I changed the index here, you know, to j, and j runs from 0 to k minus 1. There will be one term left. Okay? Because every term will vanish except when I is j. So when I is not j, this is 0. So every term will be vanished except, so this implies, so let me abuse the space a little bit. So this inequality just implies 0 equals gamma I bi q. Okay. Again, this should not be 0. If one of our search direction is 0, it just means we've hit the minimum. Okay. So without loss of generality, we assume all these are non-zero. So this implies gamma I is 0 for I up till k minus 1. So what does this tells us is the Grand-Schmidt with all previous k plus 1 vector only cares about a single vector. Okay. So the Grand-Schmidt only tracks, we only have to keep track of one vector, that is the vector in previous iteration. We can discard all of these, and it turns out it's pretty efficient. Only tracks the intermediate previous iterations. So let me talk about the homework next time. So yeah, it's a bit slower than I expected, but the next time, so we'll talk about the actual CG algorithm built upon this fact, that is the Gram-Schmidt orthogonalization procedure only tracks one set of vectors. And next class we'll also having our coding lecture, so we'll post our coding homework too as well. So now let's talk about homework. So for homework, let me first talk about problem number 1. Okay. So what I want to say about problem number 1, part A, is first of all, this is sublinear. Okay. So this P here is different from the order of convergence. Okay. So it might be confusing. So this P. So what I tried to motivate us is this P. So whenever we see this P is not the order of convergence.
So why you use the same P?
It's given, it's angle.
So why use this P to the order of convergence?
Yeah, because what I want to say is people use this P here, but I want to say if you see this P here, this P does not indicate the order of convergence.
So can't we change the letter here?
The
Can't
he's
we change the letter here?
she's saying, can we change the letter?
Yeah, you can change the letter if you want. So you can change it to Q. Okay. So this Q is not the order of convergence. Okay. So the reason is because. So I will go through this problem. The next. So the second problem is actually linear convergence. The third one is superlinear. Okay, so that's the answer, but you guys need to figure out how to show it. So this is, first of all, this goes to 0 when k goes to infinity. Okay. So by the formula, okay, what we have is xk, which is s, okay? And then we have xk plus 1 is this, okay? So the denominator is xk, subtract the limit. The top is xk plus 1, subtract the limit. Okay. What is this? This is 1. For fixed Q. Okay.
Q is fixed here.
Yes, Q is given. So by definition, this is sublinear. Okay.
Yes.
Now let's talk about problem number 3.
Wait, I'm sorry, I have a question.
Go ahead.
So are we not using that limit definition that's given?
Yeah, we're using the definition.
So x star is 0,
Yes.
and that's going to be the case for all the problems. Like x star, we're just going to say x star is 0.
Yes, for all of the problem, x star is 0. We compute the limit first, right? We compute x star first. X star is defined as a limit. Are we?
Oh, so x star is what our converge.
Yes, so the first sentence of this is suppose that the sequence converges to x star. So we need to compute the limit first,
Okay.
and then we.
Okay.
I have a question, another one. k is equal to 0. Why? It's
No, k is not equal to 0.
K
So
is
the limit.
Oh, sorry. My bad. K goes to infinity. Thank you. So number 3. Okay, number 3. Okay, so this is a 1D quadratic function. The problem is to motivate us whenever we see something difficult, we can always fall back to 1D to think about the heuristics about how this thing works. So now, for example, if we apply the gradient algorithm on this one, okay, right? So f prime is what? F prime is just x minus c. Where is the minimum of this function? X equals c. Agree? So the gradient is just how far away we're from c, right? Agree? Okay. So now if we plug in this, we get this is so we plug in this. So we replace x with xk, so we have this. Right? Okay. So now all we're gonna do is, so this is like xk subtract alpha k xk subtract, but this is plus alpha k times c. Right. So now we replace, okay? So then what we need to do is we just plug in xk plus 1 to this function. What we will get is 1/2 xk subtract alpha k xk plus alpha k times.
Would you still need the minus c and then square?
Oh,
He
Thank you.
needs c square.
my bad.
And minus c on the inside.
Yes.
Yeah.
Thank you. Yeah, you're right. Otherwise, we won't get to the answer. Thank you. So now we pull out. So this becomes 1 minus alpha k x to the kth iteration, and we pull out this one, c as well. I mean, c is x star. Okay. So by the way, x star is our c in local minimizer. So we pull out c from the second term, and we can get this is 1/2 1 minus alpha k squared x k subtract c squared. Okay. So this looks familiar, isn't it? So this implies this is nothing but alpha k squared f of xk. So we obtain formula for f of k plus 1. So we have this formula. And we want this formula, think about it. So all the f values at intermediate iterate are just numbers. Okay. So what happens is the minimum value of f, okay, is 0. All right. So this is, and we keep applying this formula. Okay. So we keep applying this formula, we will get this is okay. Okay. So if we want that number, so this is what we want. We want this quantity converge to 0 as k goes to infinity. This is a fixed initial guess, okay? Random initial guess. Then we want this. So we want this to converge to 0 as k goes to infinity. And then we use the hint. Okay. So that's so let me talk about problem number 4. I mean, in the beginning of next class. Okay. And the homework is due like the evening of next class. Okay. Evening of Thursday. So.
Thank you.
Yeah, thank you.
So he's just.
I have one. I didn't understand one part. Why k is the last part? Can you explain it to me? The why is k into infinity 0 and why we are doing this? The last part.
The minimum value of f is 0.
Okay. Yeah.
Product of all the 1 minus I squared.
Okay,
And it goes to 0 if.
Our whole gradient, decent algorithm is to let our iterate converge to this.
Yes.
Okay?
Okay, so this is like a word. So it says in here.
So we want this converge to 0.
Is in 0.
When this when x star equal to f function star is equal to 0.
One of them has to be 0. So that means 1 minus alpha I has to be 0. But if alpha, none of the alphas can be 0. So is that just like a notation? We don't really know.
This is what we want.
Yes.
Because like, I was like,
How is it possible?
how is that possible?
Say it again?
I had that question as well.
No, I didn't.
But if this converges, it has to be 0. We know it converges.
So then if we want this, it's equivalent to that. We want
Yes,
this.
yes,
Agree?
yes.
This is 0. So we want this guy converge to 0. So we want this converge to 0. Okay? Which is equivalent to this product converge to 0.
Oh,
0 in this first.
Because this is a fixed initial.
this is a fixed condition. But this is one of them is 0, right? Like the production. You've given in the question, right?
Yeah, the question is to show.
So there is a written
The
here.
question to show, yeah, this is like a square.
Yeah, it's like one of them is 0 and everything is 0.
No, it's not one of them is 0. It's their product is 0.
Is the product?
Yeah, the product must be 0. So the product, sorry, their product must be 0. So
That's what we were guessing.
I mean, if one of them is 0,
Yeah.
it already implies.
I don't really
You
know
should
about
stop.
the rest of this, but
Okay.
But
the
the product is
zero.
zero.
Yeah.
Okay.
Sorry, I have a question. Do you think I just solved this question too broad and general? Because like I figure out like because P is the variable, so I just like try to kind of like put the P
Yeah,
is
we-
less than
we-
mine or just N and
Okay.
so like order of the convergence.
So let's put a P here.
Okay.
Why that?
So this is P.
Well,
Okay.
well,
It was part
So
of.
it becomes.
part of we'll ask you. Because
It's the same as
essentially we
Q.
found- Can you
Yeah,
pull up that
but
rule on
the
your
thing
phone?
is,
It's the same.
There's like a rule.
Professor?
It's like, we know that
I
there's.
mean, I just wondered if it's correct or not.
Or like the quadratic. But then
Yeah, Professor,
we have the rule, but I put that for the later.
Agree?
Okay.
Unclear like what the rule is. to
Agree?
Take the
Yeah, sure.
negative. And so Cole found.
This goes to 1, this goes to infinity.
And
The
it
P
works,
is greater than
right?
1.
Okay, like. we
So it
found-
blows up.
but
It doesn't
then
satisfy the
all
condition.
things that, like,
So this is not correct.
included in the notes, like-
So this is not order. So this is a.
I know,
So
I know, but like, that.
so for example,
so
I'm not.
yeah,
this goes to infinity. Do you agree?
Okay.
That's
So
My question was
it's
like
not convergent.
the P was in the question like we just like figure out like if
the Q one.
Because-
Yes, the P and the Q are the same. You wrote
I know,
the-
but it's like because like you say like K is go to 0 or the infinity, then you got an answer. But for me, I thought like the P is going to like less than 1 above 1, or so you can like find the order of the convergence.
Okay. Let me try to rephrase the question.
Yes, that's
Okay,
what
so
we-
I just copied the textbook. I thought it might. Okay, so I understand now. Now I understand questions. So because I just copied the textbook, so let me rephrase. Let me rephrase the question. So just fix P. Okay.
Okay, fix P. Okay.
Okay.
Okay, fix the P.
Fix P, fix P.
Not
The P is fixed.
So
What
the
about
order of convergence is unique. It cannot be either this that. Okay.
But how do we know what it is then? Because it like depending on what P is, it changes whether it's superlinear, sublinear.
No, it doesn't.
Why?
It doesn't change.
Yeah, because we can show it, right?
The order is fixed, but below or 1 or
We
greater it changes.
so we did it in the wrong way.
Hmm?
We did it in the wrong way.
Because I think it
I think the question is really confusing.
Yeah. See.
I think like you know which parameter is variable.
Like
Is the P variable or
no.
yeah.
K is variable? You know.
So let me show you mine. What was it?
Because this
Let me.
This is what I did.
Which doesn't.
which this P is
Okay,
not the same
so-
as- that's not.
Uh-huh.
Yes.
Okay.
Like I'm.
It's not the one.
It's
Yeah.
No, because we just said those.
What we just showed is.
No, we said these conversions.
Okay. Infinity when Q is greater than 1. Okay. Agree? So this is not convergent when we put Q here. Because the definition has to be definition has to be this mu is a real number. Infinity is not a real number. This mu is from 0 to infinity, but it's not infinity. It's a real number. It's a finite number. Okay, so it doesn't satisfy the condition. It's either 3. So it's either sublinear, linear, or superlinear. It cannot be both. You change p. If you change the exponent here, you can show for each case. Then it doesn't fall into the limit. The limit is different. You have to fall. So the limit is for linear for q. So for example, so when q is 1, mu is 1. This is sublinear. Okay. When q is 1, mu is from 0, 1. This is linear.
Wait.
When q is greater than 1, mu is 0 to infinity. This is superlinear. Okay. It's one of the. I gotta go.
Oh, it's okay, it's okay. Yeah, take it out 5 minutes if you need it, just, I didn't know. Yeah.
So it's either 3. It cannot be. I mean, you can show it. So this is an exercise.
So we have to check for both.
Say it again.
We have to check for both. We have to check for both Q equal.
No. You don't have to. You don't have to argue. So here I'm telling you that it's either 3 cases. It cannot be
Both.
both or 2
Just
combinations.
one.
You just need to show one. That's it.
One. Oh, I see.
Okay.
We missed that one.
So you can show. So actually, this is a good exercise of calculus, showing it cannot be. So these cases are mutually exclusive. Okay. So this is a good calculus exercise if we want to try.